Hey everybody, so we're continuing with our derivative rules, and we're going to move into what we call the product rule. So big picture, we're trying to now move past that definition of the derivative, right? Our f prime of x, the limit definition is h goes to 0, f of x plus h minus f of x over h, right? Because we don't want to forget the meaning of it, and we don't want to forget it in general, because there are times we won't be able to use these rules, but it is cumbersome, difficult, time consuming. And so as we start to notice patterns, we can find ourselves some nice little shortcuts and formulas so that we don't have to keep repeating the same work, right? That's really what we're doing, right? When we have something like the quadratic formula. The quadratic formula is just what happens if you do the algebra to solve a quadratic equation. And instead of doing it over and over again, you boil it down to a formula. So the product rule helps us understand what happens when we take the product of two differentiable functions. So if, I'll just state it, and then we'll prove it and do a few examples. If f of x and g of x are differentiable functions, then the derivative of their product, ddx of f of x times g of x, is the derivative of f times g plus the derivative of g times f, right? So we saw when we took the sums and differences of functions, their derivative was just the sum or the difference of the functions. We hoped we might end up with something like this for products, that if you have the product of functions and you take the derivatives, you just take the derivatives of both. It turns out that this is not true, okay? And it's a really easy mistake to do, because you want that to be true. It'd be so wonderful if that was true, but it just isn't. It's not the way derivatives interact with products. So let's see the proof of this and then do a few examples. So the proof is just is a lot of algebra, really. So let's start with f of x and g of x be differentiable functions. And then we will define L of x to be f of x times g of x. All right, then L prime of x is equal to, and we're going to start as we always do with the definition. The derivative of this product function is just L of x plus h minus L of x all over h, which is equal to the limit as h goes to 0. So now I'm just going to put in the definition of what L is. It's the product of f and g. So L of x plus h is f of x plus h times g of x plus h minus f of x times g of x all over h. Okay. All right, so now here's where we're going to do a neat little trick. Okay, so what I'm thinking, I really want to see the derivatives of f and g show up in here. What I'm going to do might seem a little mysterious. I didn't invent this. I'm just copying other people's works, right? And how you should think about this as people played around with this. They manipulated it. They tried things. A lot of them didn't work until somebody stumbled onto this. Because what I'm going to do is add 0 in a very particular way. The way in which I'm going to do this is I'm going to subtract f of x times g of x plus h, and then add that same thing back. right? So all of this is still over h, right? So what I've done is inserted this 0 in between the difference in the numerator, right? So if I add and subtract to the same thing, I'm adding 0, right? So, which means I haven't changed what this thing is, right? That's the key feature there. Why we get to add 0? It's like multiplying by 1, nothing changes. Now I'm gonna imagine grouping these first 2 terms together and these last 2 terms together. And in each of these terms, I'm gonna do a little bit of manipulation in the form of factoring. So in this first term, I'm going to factor out the g of x plus h. So what'll be left is f of x plus h minus f of x times g of x plus h, right? So I factored out that g of x plus h that's in both of them, and I get left behind is the f of x plus h minus f of x. And then in the second set, in the second parentheses, the second blue parentheses, I'll factor out f of x. And what's left behind is g of x plus h minus g of x. Okay, and this is all, remember, still over h. So now we're going to do a little, you might notice where this seems to be going at this point. Notice we have an f of x plus h minus f of x, right? That reminds us of the derivative of f. And we see g of x plus h minus g of x. That reminds us of the derivative of g, right? Those are the numerators in those derivative things. We've got an h in the denominator, we've got our limits. So these derivatives are floating around there for us. Whoops, there we go. So here's the next bit of manipulation. We've got the limit as h goes to 0. I'm going to just turn this into 2 fractions. So I'll have f of x plus h minus f of x times g of x all over h plus f of x times g of x plus h minus g of x all over h. Then I can use some limit laws. I can split this limit up into, onto these 2. We've got a sum of limits is a limit of sums. Sorry, a limit of sums is a sum of limits, is how I should have said that. Minus f of x times g of x all over h plus the limit as h goes to 0 of f of x times g of x plus h minus g of x all over h. All right, now here's, oh, sorry, I miscopied something at this step. This should have been g of x plus h, which means it should also be x plus h here. Okay, now let's do one more thing algebraically. Let's just change the way I'm writing these fractions. So I can rewrite this fraction as f of x plus h minus f of x over h times g of x plus h. Right, that's just how fractions work. And then I'm going to do the same thing here. I'm going to have the limit as h goes to 0 of f of x times g of x plus h minus g of x all over h. Okay, so I've just pulled those things off and put them out front or out back, depending on which one I'm talking about. All right, let's apply a couple rules here. The product, the limit of a product is the product of a limit. In other words, the limit works the way we wish the derivative did when we have the product of 2 things, which is to say that I can just take each of these limits and multiply them together. I can do the same thing here. Over H. Okay, now we're in the home stretch. We've got, if we look right here, this is simply f prime of x, right? That's the definition of the derivative. We started with differentiable functions, so we assume this is differentiable, so it has a derivative, this limit exists. Meanwhile, what's gonna happen? Oops, that's an H. Looks like a K or something. If I take the limit as h goes to 0 of g of x plus h, right? Well, we know g is differentiable, so it's continuous. We can take that limit inside. The limit as h goes to 0 of x plus h is just x. And so this just becomes g of x. Here we've got the limit as h goes to 0 of f of x. So h doesn't even appear here. It's not part of this. So as h goes to 0, f of x doesn't care. Nothing happens to it. Nothing changes about f of x. And then that last term is g prime of x, right? That's our definition of the derivative of g. And so L prime of x is equal to this. But remember what L was just the product of these two functions. So L prime is, of course, the derivative of f of x times g of x, which is going to be f prime x g of x. And I'm just going to switch the orders of these just to match what I said. It's just commutativity of multiplication here. It doesn't really matter. And we get the derivative of f times g is f prime g plus g prime f, okay? This is the key piece of all of this, right? We don't at this point need to be able to come up with this proof, but what it does for us, what this rule gives us is now when we expand our definition, our derivatives, and we start combining functions through multiplication, if we can take the derivatives of the functions individually, we end up with something, there's a simple way to take it, whereas reverting to the definition, the limit definition might have been very, very complicated. Let's do a couple of quick examples, okay? Let's start with a pretty abstract example. So let me write the rule again. If we have dx, f of x times g of x, we're assuming they're both differentiable. I'm just writing the most relevant part to what we're doing now. F prime g plus g prime f. So let's suppose f of 3 equals 2, f prime of 3 equals -3, g of 3 equals 3, and g prime of 3 equals -1. Okay, so this is assuming we have some functions and we happen to know a couple values and the values of the derivatives, right? There's lots of reasons why this might be true. We might have been doing a big problem with lots of different pieces, and at some point we already had to compute these. And so we're at a place where we might want to compute if L of x equals f of x times g of x, find L prime of 3. Well, what we know is that L prime of 3 is going to be the derivative. So if we take the derivative of L of x, it means we're taking the derivative of f of x times g of x, which means L prime of x is equal to f prime of x, g of x plus g prime of x, f of x. Which means that L prime of 3 is equal to f prime of 3, g of 3 plus g prime of 3, f of 3. And we have all these values. F prime of 3, I'm just reading from above, is -3, g of 3 is 3, plus g prime of 3, which is -1, and f of 3 is -3. So we get -9 plus 3 or -6. And so L prime of 3 is -6. So we're just applying the formula in a straightforward way. This is part of what we have to do, right? We just need to be able to look at this formula and understand where all the pieces go and be organized about it. Let's do another couple of examples that might help illustrate that. Let's suppose, let's let f of x equal x squared minus 1 and g of x be equal to 2x. And we'll define h of x to be f of x times g of x. And we want to find h prime of x, right? Well, according to the product rule, h prime of x is equal to f prime g plus g prime f. So let's just write out all the derivatives and functions we need. We've got f of x equals x squared minus 1. So f prime, I'm applying my power or the sum rule. I'm going to take the derivatives of x squared and -1 separately. The derivative of x squared by the power rule is 2x. The derivative of -1 is 0 by the constant rule. G of x is equal to 2x. G prime of x, I'm applying the constant multiplier rule, means that constant 2 can just stay out front, and I'll take the derivative of x, which we know to be 1. So we get 2 times 1, or 2. So there's all my pieces. H prime of x is equal to f prime, which is 2x, times g times 2x, plus g prime, which is 2, times f. Can do a little cleaning up. I've got 4x squared plus 2x squared minus 2, or 6x squared minus 2. And there's our derivative. Now, you might think to yourself, or you might notice, wait a second, we could have done this a little differently. If h of x is equal to f of x times g of x, that means h of x is x squared minus 1 times 2x, which is equal to 2x cubed minus 2x. We can just take this derivative directly. We don't need to use the product rule here. We can multiply it out, and this should be fine. The product rule can be true, but this is also an equivalent way to write this function. So what happens when we take the derivative this way? Well, we use that constant multiplier rule, so that 2 is going to be out front. I take the derivative of x cubed. I use the power rule and get 3x squared. And then this minus 2x, we just took the derivative of 2x a second ago. We've just got a minus now. It's minus 2. If we multiply this out, we've got our 6x squared minus 2. So of course, they work out to be the same, right? Both of these rules are valid. And so we can apply either one. There's no better way to do it. Either one of these is a legitimate way to compute this derivative. Remember in the previous video, this is exactly what led us to realizing we needed the product rule. We tried to take the derivative by just taking the product of the derivatives, and we got something that didn't agree with our other method of taking it. And so now we have nice agreement. Our rules match up, and this should always be the case. Mathematics needs to be consistent. And so if we have two appropriate rules, they better lead us to the same result, or at least one of them has to be incorrect. Okay, let's do one more example of the product rule. Actually, let me say one quick thing about this, right? I would typically do this one if it were me. I probably would default to doing it this second way more often than not, right? Which makes the product rule feel a little bit superfluous here. And it kind of is at this point. We don't have a lot of derivatives that we know how to take yet. But as we start gaining them, right, because we mostly know how to do polynomials. That's really all we know how to do with our shortcuts. And if you multiply polynomials, you get more polynomials. So you don't really need a separate rule. You can just keep multiplying them together and then using the polynomial rules. And so the product rule doesn't really give us anything new yet. Where it'll start to get interesting is once we start adding things like logarithms and exponentials and trig functions and so on. When you multiply polynomials times a trig function, you don't get another polynomial. So you can't do it any other way but the product rule. Or when you have an exponential times a trig function or a logarithm times a polynomial, right? All these combinations, all of a sudden, once we get all those, this product rule becomes crucial for us. But even with just polynomials, there are still cases where it might be useful to use the chain rule. Here's an ugly looking polynomial, right? We could multiply this out and get a big polynomial, right? It would be a degree 6 polynomial, so it might have 7 terms and it would take a lot of cross multiplication. And that is a valid way to do this, but I want to do it with the product rule to show you another route. So we're going to take the derivative of x. So we're taking the derivative of this chain of quantities. Okay. So the product rule tells us what to do when we have the product of 2 functions. Seems like we have the product of 3 functions here. However, there's nothing wrong with thinking about this. Let me do it a different way. Let's think about this as one function, and this first one as our second function. So then the product rule tells us what to do. Take the derivative of the first function and leave the second function alone. Then leave the first function alone and take the derivative of the second function. All right, so in my colored notation, I've got a red function and a blue function, and I'm taking the derivative of them. And the product rule tells me you get the derivative of the red function times the blue function plus the red function times the derivative of the blue function. Okay, that's our product rule right there. Instead of using f and g, I'm just using little circles to represent these functions, right? But that's what our derivative, our product rule tells us to do. I'm going to leave this written this way for a second. We know how to take this derivative, but we're going to leave this alone for the moment. And we've got, maybe let's do a little coloring here. So here's the derivative of the red. Here's the red by itself. Here's the blue function and the blue function. All right, so these are left alone. All right, now I've got to take this derivative of another product of functions. There's nothing wrong with doing the product rule again. All that I need to do is take this derivative. So if we forget the rest of the problem, if I pretend for a second that all of this isn't here, and I was just taking this derivative, if I gave you this, you go, oh, I can use the product rule here. Well, just because there's other stuff happening doesn't mean the product rule doesn't apply. So I can take this derivative using the product rule again. So now I'm going to use the product rule and put it all inside these brackets. So what does the product rule tell me? Once again, I take the derivative of the first function and I leave the second function alone. And then I leave the first function alone and I take the derivative of the second function. All right, we're almost there. We're going to start taking derivatives in a second, but I want to do one more step. So I'm going to leave this derivative for the moment. There's our derivative. The other two functions are left as is. All right, so now I want to multiply. I'm going to distribute this thing here. Okay, so when I distribute this, I'll get x cubed minus x times these two, right? I'm going to just swap the order of them. No, I'm not. I'm going to leave it as written. Sorry. ddx, 3x minus 2, and then x squared plus 1. Plus, I'm multiplying this, distributing this again, x cubed minus x times 3x minus 2 times the derivative of this last piece. Okay, let's do another little round of color coding. Let's pick some new colors. Let's get a purple in there, maybe an orange. How about a magenta? All right, so let's just name these functions magenta, purple, and yellow, or orangish. Okay, let's see what we ended up with by the end of all of this. We have three functions that I'm naming with these circles: magenta, purple, and orange. Magenta, we have the derivative of the magenta. Here we have magenta by itself. Here we have magenta by itself. Then we have the derivative of magenta times purple. Then we have the derivative of purple. And then we have purple again. Finally, we have this, let's call it gold. Gold, nothing's done to gold. Nothing's done to gold here. And then we've got the derivative of gold. And we're adding those three things together. Right? So look at what happened. Each function took a turn having its derivative taken, while the other two were just themselves as a product. And then the next one gets a turn having its derivative taken, while the other two are left alone as another product. And then the last one has its derivative taken, and the first two are left alone. And then we take that product and we add those three products up. Okay. This pattern keeps going if you have a product of 4 functions, of 1,000 functions. All right, so we could let's finish this problem and then we'll summarize this in a little more clean notation instead of colored circles. So now we can take this first derivative is, we use the power rule, 3x squared minus 1, 3x minus 2, x squared plus 1. And we've got x cubed minus x. The derivative of 3x minus 2 is just 3. And then we've got x squared plus 1. Then we've got x cubed minus x. Sloping up a little bit, 3x minus 2. And then the derivative of x squared plus 1 is just 2x. And there's our derivative of that function. Okay. Obviously, we could expand this if we needed to. It just depends on what we're doing next, what we might want to do with this thing. There's various ways we could approach how to deal with this thing, but I'm just going to leave it as is for now. This is a perfectly reasonable way to write it down. So we can generalize. Let's just write it down for 3 functions. If I have f of x times g of x times h of x, and I take the derivative, I get f prime plus f of x, g prime of x, plus f of x, g of x, h prime of x, right? That's really what we just showed there, what we did. And this works out as if we went to 4, we'd have to have we'd have 4 terms in our sum because we'd have to have more, another one getting its derivative, but each one just takes a turn getting a derivative while the other however many are left over are left alone, and then we add up all those products. Okay, that's it for the product function. We will certainly revisit this. This is a really useful one for us that we will use over and over and over again, but we'll revisit it when we get into a few more interesting derivatives like the trig derivatives in a couple videos. Okay, thank you everybody. I will see you next time.